Hello everyone, welcome to the Project Application Webinar series on Midas Civil. Today's topic is going to be pre-stressed concrete multicell box girder railway bridge built with balanced cantilever method. First, let me introduce myself. My name is llic. I come from Banja Luka. I have graduated structural engineering at University of Banja Luka, Faculty of Architecture, Civil Engineering and Geodesy. I have more than 11 years of professional experience in infrastructure projects. My main focus is on bridges, road, railway, and pedestrian bridges and retaining structures. My current company is BCE from Banja Luka. Here we have a table of contents for today's webinar. I'm going to introduce you to the bridge type and modeling methods used. Also, we will talk about design code, loads combinations, boundary conditions, and post-processing. This bridge is part of European 5C route in Bosnia and Herzegovina. Approximate length of this bridge is 640 meters. Superstructure is designed from post-tension concrete, C40. Piers and abutments are designed from reinforced concrete, C35. The interesting thing about this bridge is that it contains 3 parallel train tracks. Actually, it is a train passing loop. There is a railway station in the near of the bridge. Maximal pier height is 68 meters. Here you have two cross-section views. On the left you can see cross-section at the midspan, and on the right you can see the cross-section at the support. As you can see, it's a multi-cell actually. The box girder has 2 cells. At the midspan, height of the box girder is 4.5 meters, and at the pier it's 8.5 meters. Total width of the superstructure is 17.3 meters. Finite element model of the bridge is made in Midas Civil. The software supports construction stage analysis, time-dependent concrete properties, long-term post-tension analysis, seismic analysis. Model has been simplified for presentation purposes. Only global analysis is performed and general section design is performed for this presentation. Some key presentation points are application of rail traffic actions according to Eurocode, application of seismic action according to Eurocode 8, generating and interpreting results in Midas Civil, and pre-stressed concrete superstructure design according to Eurocode 2. Now we're coming to the part of the webinar where I'm going to show you how to define materials, how to define cross-sections. I'm going to show you how you can use free cantilever method wizard for generation of model, and also additional tendons which you can import from one model to another using Midas Civil MCT. Final product is going to be bridge model that you can see in this picture. You can also see here finite elements numbers that I've been using for this concrete bridge. Okay, so here we have our Midas Civil window with materials and sections imported from similar bridge project. So you actually don't have to go and manually enter materials and cross sections every time. You can just import it from some project and reuse it and change it accordingly to your new project. So general procedure is to define here. Click on material properties, you click on add, you define material ID, you give it a name, choose from database, let's say steel, and here we have numerous options to choose from. Let's say for tendon, you can see the grayed out values. You can check if everything is like you want it to be. This part we're going to skip because we don't need it for our project. And if we are satisfied with our input, we usually confirm it with OK, but we won't do this now because we already have the material defined for piers, for superstructure, concrete C40, also for tendons. You can see here all the values we need. After we define the materials, we can jump to cross sections, which can also be imported for foundation, for pier, for tapered superstructure sections, for diaphragm also. We have two cells, bridge box girder. We also define here time-dependent properties for our concrete, C40, compressive strength 40. Other values we leave as they are. Notional size of member is actually best to keep it 0 here, because after program has a very nice option to calculate notional size for each cross section accordingly to its dimensions. And here we can check what have we gotten. Okay, looks fine. We can apply it, and you can see here the blue. Blue actually means that our definition is not used. It's not applied in the current model. Here I can also add time-dependent material, compressive strength. Also I can name it, for example, C40, choose European, mean compressive strength is 40. And if we click on withdraw graph, we have a nice graph which you can import later in your report. You can name it here. If you say OK, it's going to be saved for later use. So previously I have shown you how you can define manually the sections, but also the bridge wizard handles the section creation, where you can choose your type as one cell or two cell section. And also, this is by now it's familiar to you. These are parametrical dimensions for the cross section. You can see how does it look in midspan and also at pier section. And here we have this sketch with parameters. Here you have a very convenient option to include the wet concrete load. Actually, the program automatically calculates the formwork, weight, and takes it into account accordingly with each stage it creates. Here you enter the formwork traveler weight, and also you enter the eccentricity for the formwork itself. In this tab, you define the tendons. You choose your tendon property, which you have previously defined, and also you can limit the stress at the pre-stressing. So basically, you would like to choose 85% of the yielding strength, or 75% of the ultimate strength according to Eurocode. Here you define the position of each and every cable. So basically, if we know that we have these 11 parts of the free cantilever method, which includes zone 1, this table part, zone 2. So if we have these 11 parts, let's say that we need maybe 6 cables per part for each stage. That means that we're going to need 66 pre-stressing tendons. If we click here, we can define the necessary number of the cables. So I set it to 10, but even if you put a small number, after you define tendon anchorage number, the program will automatically add the necessary number of tendons. So actually, it's good for you to define this correctly, but the program will also correct you if you make any mistakes here. Same goes for the bottom cables. Define anchor numbers on the sides or in the middle part. Here you can choose the top tendon routing if you want with each pre-stressing step or every 1 stages, which actually means when you, for example, pre-stress the cables in the first step, the program will consider that it's routed in the next. So basically it's quite simple and straightforward. After you define all the parameters, you simply click OK, and the Midas software is going to generate your model. In general, free cantilever method is one of the simpler models to create. With Wizard, it's extremely fast, but if you don't use a Wizard, you will lose some time for defining the construction stages, for defining the correct cable geometries. But you will have also more control. Generally, I like to use the free cantilever method bridge wizard for my starting model, which I can later upgrade or build on it, because it defines all the necessary elements that I need. So as I've mentioned before, we're using Eurocode in all aspects of the design for this bridge, and only global analysis is performed, and general section design is performed for superstructure only. So here are some standard elements of standard values for the concrete that is used for generally used. Here are our values of interest for our superstructure design. So here we have our bridge model. The difference from the model that is generated with bridge wizard is that here I have defined some additional loads. I have defined reinforcement for cross sections. I have added time-dependent properties for the concrete material, and also I have applied actually tapered sections. So you can see basically how our model looks like. If you choose any of the elements you can actually isolate it. You click on activate, or I prefer to use the shortcut F2. Here you can see how it looks. If you don't like the wireframe display, you can turn it off too. There is an option to show all, activate all. You can also see some other parts, for example. Let's say I want to see it here and the bridge diaphragm. So this is how it looks like. You can see the opening we defined, so everything looks okay. Now, after the wizard has generated the whole model, usually you want to check what it has done exactly. So here, for example, you can find your construction stages. You can see for each stage which groups are activated. All of these groups are automatically generated by the wizard and are necessary for the construction stage, so you can effectively activate or deactivate some of the elements, also boundaries, also some loads. For example, you want to have groups for tendons, so you can easily activate multiple tendons by calling just one group. And also, for example, you want to have your groups for form traveler, so you can turn it off or on when you need it. But this is actually everything handled by the bridge wizard. You can see here construction stages. Out of these 18 construction stages, wizard has created these 17. I had to define manually the construction stage for long-term effects here, and also I had defined an internal step inside of the construction stage 18. So this step here actually is very important for me, as I consider that 19 days after ending of construction stage 17, my superimposed load is going to be activated on my structure. Here I have my ballast, I have my rails, and other loads that are considered dead weight, but that are not structural elements. So discuss the results, you're going to see that most of these construction stages have multiple steps. Usually you have first and last, but if you define intermediate steps, you're going to see them also. Usually the first step is step when you activate the dead loads and pre-stressing, while the last step takes into account all the shrinkage and creep that happens from the start of the stage by the end of the stage. So here you have a nice overview of each group that is activated. Group 1, peer 2. So basically you can, as you understand it, in construction stage 1, all the substructure is activated here. In construction stage 2, we have our segments, and we say they are 7 days old when we take down the formworks. Also, if we stay in the same construction stage and we jump to load tab, you can see here that the first day form traveler is activated, wet concrete is acting up to 7th day, so it is corresponding with the age of the concrete. And also you can see pre-stressing groups here. As you have 5 pairs, for each pair you have 1 pre-stressing group. So PS1 is for pair 1 and -1 means that it is pre-stressing the first segment. Also on the right you can see which loads are deactivated on the first day of the construction stage 2. You have form traveler for the little part and wet concrete. So it's the same actually for all the rest. You can also have to take precautions when to activate which support or other boundary conditions if you have them. For example, support for foundation is activated in first construction stage, and you also have elastic links between foundation and bottom of piers. You might not actually see them now because they are not shown, but you can easily find it in display properties, boundary, and look for rigid link. If you apply it, you will see that you have here rigid link that has rigidity tendon fill 3 translations and 3 rotations. So it goes like X, Y, Z translation and also X, Y, Z rotation. Okay, we can turn this off. So if we go back to works, now we can look at our tendons. And it says here we have 590 tendons. It really is a lot. But actually it has a really nice logic behind it, so it's easy to follow everything. For example, what are you interested in the beginning are these top tendons. So we said that we are going to have 6 of them for each segment. We select these 6 and we display them. And if we zoom in, we can see its profile and also this direction. Okay. So after running the first calculation, I have seen that after a few stages, these cables that run through the top plate of the box girder are not enough for me to satisfy the tension limit in concrete for construction stage. So I had to manually add some web tendons, and I used the same logic. I named it web. Web 01 is for tendons that are on pair 1, and 1, 2, 3, 4, 5 up to 6. These are the 6 tendons I have modeled here in the web. So basically this is what you get. Two tendons in each of the web. Now, good thing about using wizards is, for example, you can only, let me go back into the window with the wizard. For example, you can see here when wizard had finished, it had all the PSC lines, so you have to work on it. You have to define some additional nodes and elements to make it more realistic, as I have done it in later model. Here I wanted to show you, for example, if we use wizard again, we can define additional tendons. For example, in the first one, let's say we didn't provide full staging method tendons. For example, like this is here. Or for example, we provided only top tendons and none of the bottom, which would be, for example, N6. We can easily change any of these parameters now. We could say OK, and we could rerun the wizard. And after everything is created, we can open this very powerful tool, text editor actually, for Midas Civil. It's called Midas MCT command shell. It's actually some kind of scripting language for Midas Civil, and very useful too. Here you have a lot of commands. It really doesn't tell you anything at first, but after using the program for a bit, you really start to see all the power it has actually. For example, by now I know the tendons profiles are command is tdn profile. So here it finds it. When you start to type it, it offers you whatever is more similar to what you're searching for. And for example, if you have some generator for your geometry, like you can easily create something in Excel spreadsheets, so it generates this code. It's really good for fast generating of some typical tendon profiles. But here I will clear this. I will say insert data, and here you will see all the cables it has in this model. These are all pre-generated by the wizard. So for example, these top are not interesting for me as I already have them. Maybe I would like to add maybe these two cables to my other model. I could easily just copy it, open my other model, find MCT command shell, and here I'll type in profile, insert command, and then paste it, and simply then click on run, and it will add these two cables. I will not do it now because I have already defined them here. So not to make any, just to avoid maybe some possible errors if I have changed some of the profile elements. So basically you can see that this MCT command shell is really powerful tool and really is helpful, especially when you have a lot of similar bridges where you can use a lot of elements. Actually, you can import anything using it or export anything by using it. Let's say, okay, let's say we want to export properties for the tendons. If we click on insert data, you will see the name. You will see that it is internal type of tendon. You will see the area of the tendon, duct size, also values for ultimate and yielding strength of the steel, slip in millimeters. You always have to be very cautious when you import or export these elements, so that you're always aware of which units you're using currently and which units are set in the model that you are importing to. Okay. So for loads and load combination, we find everything according to your codes, as we have mentioned it. So we have the value of almost 270 kilonewtons per meter of length of the bridge for superimposed loads. Also, wind load is defined according to Banja Europe provisions. We define the length, the width of the bridge, and we also interpolate the wind effects on the bigger section near the pier, all across the lower section in the middle span. And generally we have two load cases. We have wind on the bridge without vehicle, where it has 21.65 kilonewtons per meter near the pier and 9.54 near the midspan. And also we have wind with the vehicle, with traffic. This is 35.27 at the pier position and 23.17 at the midspan. So basically everything is modeled that way in the Midas Civil. We can show it here. So we go to static loads, and let's say we want to see wind effects with traffic on. So this is looking pretty bad at first, but when you zoom in, you can see that you have actually, okay, let's maybe isolate some elements to make it a little bit more appealing. So now you can see actually that we have lateral force of the wind here 23.2, with at the same time we have only one load model 71 with psi factor, so it's 80 multiplied by 0.8. And if you want maybe to check another position, let's say, okay, let's see what is number here, 18. You can easily see, maybe this view is the best, how the wind load is changing accordingly with the cross-section height. Sorry. So as you can make it linearly or parabolically change along the length of the bridge. You can also set the eccentricity for it accordingly. So as you can see, the line of the wind load is falling down. This is actually positioned at the center of the area, bridge section combined with the height of the train. Okay. Also here we have defined wind loads on the columns, where you can see that it changes accordingly with the height of pier, which is okay. Okay, so this is actually, I have like this only to show you that you can, all the loads that you have actually in Midas, or actually any data in Midas Europe, is easily copied into and from Excel. So let's say you want to edit something. Let's take, for example, this wind with traffic. You can easily go to loads, load tables. Here you will find static loads and you search for beam loads. As you can see, all your elements are here, all your load cases are here. If any load case has defined eccentricity, offset, direction, and here you have the values. Also, if you have defined the group for some nodes, it will be shown here also. And everything you can click in, change, copy, paste, just like any regular spreadsheet. Here you have drop list, you can choose to apply whatever group you want to. Also, you have some helpful tools. For example, you want to sort it to see all the load cases sorted together, and you can see it here. Superimpose load, then you have your wind load, then you will have your wind load with traffic, and so on. Here it is. So when you get used to these tables, you can work really fast and be very efficient with your modeling. So for temperature loading, also according to Eurocode, we have our input temperatures, shaded minimum temperature, shaded maximum temperature. Also we have components of temperature difference for heat and cool. And also we have combinations of these two values, but actually we have chosen this approach for the box girder, and also you can see it in Midas how we modeled it. So usually for temperature difference, when using box girder bridges, it is very convenient to define one case manually and then just copy it along the tables and reuse it. As it has really a lot of data, it's a big table and sometimes it takes some minute or two to generate all the data. But even in that way, it saves you really a lot of time. So this is how this table looks like. A lot of maybe at first sight a lot of unfamiliar cells and values, but it's really easy to get the logic how it works. Basically, for the first temperature, it's best to use this beam section temperature, where you can say, for example, I want my case to be temperature T1. I can leave the load group default, and I choose section type PSC composite. I have this checkbox applied by code provision, which is really helpful because you just choose your code and you choose, are you taking temperature difference or gradient by heating or cooling. We have this table provided also from our Eurocode. You can enter the values and you leave this auto if you don't want to hassle with all the changes in the cross section. So the program actually does it for you. It recalculates everything accordingly to each cross section. Or if you have something simpler, you can choose to enter it manually. So basically what we are left with is we need to define our train loads, because we have 3 rail tracks at once in one bridge. It's actually a little more complicated than usual to set everything up. As I have already run some calculations on this bridge, I know that unfavorable case will be for bridge model 71 in options when it's loading only 1, 2 or all 3 rail tracks at the same time. So everything is according to Eurocode. I will not really go through how to get all of these values because it will take some time and it's not the theme of this webinar. So about the moving load now. Here at the load tabs you have moving load. Usually your first step is to define traffic line lanes. So you will turn off here all the loads and all the tendons on display. So, okay. First, you need to choose moving load code. You have abundance here to choose from. We will go for Eurocode. You have some options here for defining definition of traffic lane. When you are dealing with road bridge, you have this nice option, moving load optimization, where the software itself internally sets up the worst positions for the load, so you don't have to hassle with it. Now, here you see I have defined 3 rails. I will not delete anything, I will just show you how the window looks like. Lane width is not very important here when we are dealing with the rail bridge. Eccentricity we leave 0. Wheel spacing is actually also not so important because it's defined in the vehicles. What is really important is to choose correctly. If you're dealing with line model, like this is line model, you have to choose lane element. And if you are modeling a bridge using plates or grille system, you need to choose crossbeam. After you select all the elements that you want your train to run on them, you simply click add and rails are created. And I'm going to show you how does it look. Let's zoom in here. Okay, line lane, apply, and you can see actually real 1, real 2, real 3. The trains can run both directions in case you haven't noticed. It's an option that we can select here, moving direction both. Okay. So the next step would be to define the vehicles. We have standard Eurocode vehicles for railway bridges, and it's quite easy to add them or edit them if you need something different. Here we can choose road bridge, footway. You also have here fatigue models offered and also rail traffic. You can take into account eccentricity, usually it's 0.08 meters, and other parameters defined by Eurocode. The same is for the others. You just simply enter the name for the vehicle and choose from the database. After you confirm everything, you need to define moving load cases. So this is very interesting part for the bridge with a passing point or passing pool. So generally you have a lot of options here when you have 3 rail tracks. For example, if only one train can be on the bridge at one moment on any track, actually 2 bridges in any combination, and 3 bridges when they are multiplied by the factor of 0.75. The same goes for the load model 71 and load model SW0. The heavy load model, train model SW2, is specific because it can the bridge can be loaded only by it in cases where it is acting alone on any of the 3 tracks, or it can act simultaneously with load model 71 or load model SW0 at the same time. So in this option, only 2 rail tracks can be or should be treated or loaded. I have here modeled only, actually I have shown only load model 71 because in my more detailed model I have run the analysis for all of these, and the conclusion is that this is the load model that is actually giving us the most unfavorable effects. So you can here see that it has 5 load cases. So there is a really nice option in Midas Europe for simultaneously loading multiple rail tracks, so that you can create actually only one load case that is going to incorporate all the 5 load cases or all the 5 possibilities of positioning load model 71. So let's see how the software does it. Okay, you name it, you describe it, you say it takes into account these 5 cases. This is just a little note for yourself. You don't use this because the bridge is for rail traffic and trains have fixed point. They cannot move laterally unless they have additional crossings, unless, for example, the client has defined. So in this case, Sorry. In this case, these lateral movements of bridges are done before the bridge, so we have 3 fixed positions for the trains. Here we choose railway bridge. Under the railway bridge data, we can choose to ignore psi factor. This is because I want to manually later edit some of the combinations, but in general, if you use automatical generation of load cases, you will want to create one case with C factor and one without. Also here you have this multiple presence factor for load model 71 and SWO. When you have number of loaded lanes for 1, scale factor 1, for 2 it's also 1, and for 3 or more loaded rails it's 0.75. We confirm this, and here, because we have only one vehicle, we click on add and this window will open. You choose your vehicle, scale factors, minimal number of loaded lanes and maximum number of loaded lanes, and usually these 3 are here. You choose them, and in this way you're saying to the software, okay, my reference load model is load model 71. It can go on 3 rails. Minimum number of loaded lanes is 1 and maximum is 3. If it is 3, it's going to use that factor provided 0.75, and if smaller number of lanes are given, it's going to combine them in the way that is going to cover every position with only 1 train or with 2. So the software really saves a lot of time for you when you're dealing with a little bit more complicated case of rail bridge like this one is. So generally, when this is defined, you can also take some time and simply see what have you modeled until now. So if you, for example, go to materials and you double click on material for bridge girder, you can select it automatically and just isolate it. And let's say you want to zoom fix for stages. It means that the window will remain the same size during the overview of the stages. So let's start with the construction stage 2 because it's the first stage that actually has superstructure in it. So during the phase 1, bridge piers are made along with the bridge diaphragms. Here you can check how the bridge is. It's like a little simulator for the bridge construction. So everything looks okay. If you want, you can, for example, show the loads maybe from traveler during the changing of the construction stages. Of course, you need to adjust the units. So you can see, maybe you recognize this value from the wizard previously. And also you have, this is vertical load, nodal load vertical, and this is moment, which is generated by this vertical load on the provided eccentricity of 2.5. Maybe I can show it here. In the bridge wizard. Okay, here. So this is the force, this is the eccentricity, so everything adds up. So this is the load from the foam traveler. And if you want to see how the software manages tapered section weight, you can also do that. I will show you. Okay, using the same procedure, you just need to select it here. So for example, let's start from this stage. You can see the weight of the concrete as vertical load, and the moment it generates. So if you go through the stages further, you will see how it changes accordingly to the variation of the section. So in this part, Wizard is really helpful, and I really recommend it to use, because it saves really a mass of time by generating these little, or automating these little boring stuff that you know, and it's really easy to make, but it's just repetitive task, a little bit boring. Midas really makes it easier for you to generate it, and you can focus and spend your mental energy on reviewing the results. So I need to also mention the boundary conditions. So for simplicity for this presentation, I have made all the supports for the piers fixed. And also here I have modeled, just a second, I will show it to you, supports and also elastic links. But we need to show it in base. We will turn off any loads. Okay, so you see we have elastic links type rigid between superstructure and piers. So you have maybe noticed that there are two types of links that can be rigid. We have rigid links that only connect elements, and the elastic links type rigid are different because they can actually show you forces they are transferring or deformations. So we use them also to connect parts of the structure, and for example here we used it to connect superstructure end to the positions for the pot bearings. Important thing about any of the boundaries is to be careful about assigning them to proper groups so it can be activated in correct stage. You see, for example, supports for the bridge piers are in support group, while the Pot bearings are actually in some group that is going to be activated much later. Let's see, for example, maybe, let's see here, boundary, okay, they are still not activated. So actually, pot bearings are activated in construction stage 13. So this is why it's very important to be careful when you assign your support points to the groups. We haven't mentioned yet the seismic loads. With Midas Civil, it's really easy and straightforward to define excitations, seismic excitations. So we will be going to be using the response spectrum analysis. We have option under the load tab in dynamic loads. We have as response spectrum functions, where you can easily add appropriate spectrum function. So you can actually here choose between spectral data type for normalized acceleration, for acceleration, for velocity, or for displacement. And if for any reason you can change the display type for this graph. You have different scaling factor, which can come in handy for behavior factor if you need to use it. Here you can choose which type of ground you have, what is reference peak ground acceleration, define the importance factor for your structure, damping, and maximum period. Here you can use recommended national annex or Singapore for now, but more annexes is coming with every new release. So after defining the response spectrum function, next step is to define response spectrum load cases. You name, for example, if you want to analyze only horizontal directions, you will write here S6 is acting in plane of XY, angle 0, and you simply click on add. The same way you define the other direction, the difference is only this is 90 degrees bigger excitation angle. And with these simple steps, you have defined your seismical loads for your bridge model according to your coordinate. So now we can save our model. Good habit is to save frequently, like in any other software. You never know what might happen during the work process, and you don't want to lose your progress. After the file is saved, we're going to run the analysis, which usually takes, well, up to 300 seconds. For first, very important thing, before running the calculation, we have forgotten to define notional size for our sections, namely our superstructure. So we will choose by double-clicking on corresponding material. We will choose auto calculate option for notional size members. So I think I have previously done this for this model, so it should be available in tabular form as it is here. So this is very important for creep and shrinkage calculation. Okay, now we have everything we need, so we can freely save one time more, just in case. And we are going to run our analysis. So our calculation is done, quite fast actually. Now we can actually take a look at the results. Are they the ones we are expecting, or are there some illogical things, or maybe we need some corrections regarding maybe tendon profiles, forces in tendons. Generally, I don't expect any changes in bridge geometry to be necessary. Main focus is on the superstructure, so it is adopted by the recommendations for this type of structure. So it should be fine, except maybe perhaps we will need some tweaking in the tendons profiles or forces. So let's dive into it. For the start, we want to fixate the zoom for the stages and also member activation fix. This is done by first isolate the members you want to, or elements you want to look your results for, and then click on fix. Now we're going to choose from results stresses, beam stresses for PSC, and because it's rather long dialog box, we're going to minimize the ribbon so we have room nicely for, so we don't have to scroll down and up after every stage or something. Okay, so firstly we will choose section position. We will, because it is a straight bridge, we should probably have same values on both ends. On the top slab of the box cross section, here we choose component for stresses. We are very interested to see sigma xx summation, so all of these components together. Field type is not very important to us. We can maybe enlarge the scale factor just to have more radical view option here. Legend details. Okay, so I've set the legend. We have two decimal numbers. I don't like the units. We want to see Newton per millimeter square. So actually megapascals. And here values, turn them on. We will set the orientation of the values to be 90 degrees, and we'll choose minimum and maximum only. So this is what we get. We can here change if we want. We can change the fill type. We have options for solid, line, or no fill, which is maybe the best for current viewing situation. Here we can start to take some look at these structures of ours. So at the construction stage, where these this superstructure is built by a free balanced cantilever method, I don't actually expect to have any difference in point 1 and 2, so we're going to observe only position 1. Starting from construction stage 2, as you remember maybe, I have mentioned that internally every construction stage has its own steps. Here you can see this, how this actually practically works. If we choose user step 1 and we apply it, you will see that some little changes in stress values have happened. This is because some form traveler is removed or some wet concrete is poured. So this is why it happens. And the last step, you have maybe sometimes none of the changes. But the important thing is that we have not pushed our structure over the allowed tension in concrete for construction stage. Okay, we can simply go further. So we can quite fast run through this by just changing the phases. You can see that we are quite safe here with our values. Just follow the legend, or if you prefer, you can see also here the values. Also, the diagram has pretty expected shape. So everything is good here. You can see how structure is coming to closure with no tension in the top fiber. Maybe here at the end a little, but we didn't actually model it really 100% correctly. We just left here the section from the midspan, but it's not a big mistake. It can be easily edited. So at construction stage 13, after this we expect it to fit the key segment and to connect our superstructure. So this is coming right about now in construction stage 15. So the first step is with the formwork traveler active wet concrete. Then we have pre-stressing and concrete stiffening or concrete curving. So we come to the, here we have this construction stage 18, which was added by me manually. I wanted to see how everything will behave during the time of 30 years. And also I wanted a construction stage in which I can add my superimposed load. So at the first step here, this is, so let's say, how old is our structure now? So well, according to my calculations, and it could be 192 days. Yeah, well, it depends actually. This is just assumptions that the constructor will have so many formwork travelers. It could be actually that they have only one pair, so they can be building only one at a time. So, but this is easily, I mean, when it comes to construction, the construction can contact you, and using the Midas you can really easily adjust everything from the dates to the real actual properties of concrete used. Okay, so what we want to see here now, what happens when we add superimposed load. Okay, so it doesn't make sense. No tension. This is how we want it to be. And after 30 years, you can see the diagram of normal stresses for the top fiber of our box girder bridge. So we would like also to know what's happening at the bottom here. So already at first stage we see that we have some tension, but it's far away from the allowed, so we are safe here. We consider it to be okay if allowed tension in concrete is not surpassed during the construction stage. Okay, now we will take a look how it develops. This is quite well now. We have at the time of closure, no, it's not closed still. Okay, now we have some values that need to be taken into account, but probably I expect most of it to be covered when superimposed load is applied. And let's see, construction stage 16, first step, last step. Okay, there is distribution of stresses happens during the creep shrinkage. Here we have this spike 1.3. This can also be, well, let's see. Let's build the bridge to the end and then we will consider it. Okay, it's still here, 1.22. Some tension has been left over behind. So the easiest way to deal with this would be to actually maybe alter a little bit the tendon profiles, or even we can put more jacking stress at the start of pre-stressing. So maybe we can see how much we have room for overstressing, or maybe safer, more conservative approaches to adjust the profile of the tendons in the area. So it's in the part of the, yeah, it's on this. This is really not a problem. It can be easily managed. Okay. So let's see. In post-construction stage, actually we have some maybe interesting options to show it to you. So for example, let's take beam diagrams, and for, well, it's not really important, but let's take envelope for the moving load. We can apply it because these are diagrams for moment. We want it to be shown in kilonewton meter. So for example, if you want to have some different options for preparing your diagrams for report, one of them is to use dynamic report image, where you can save current view with current settings and use it later in the report. I will not go into detail about the report, but I'll just say it's a really useful feature with everything being dynamic. Like every table you have here, every diagram you make, every chart also, for example, everything is dynamical, so if you change anything and you rerun your calculation, you can easily update everything. This option is now gray because we haven't created our report generator, but it is something you can find online on Midas IT YouTube channel, for example. And also you can here define, for example, let's say my and fz here. You can batch plot for any load case actually you want to. Let's make only for temperatures here into this folder. We don't want to have too much of the pictures get generated. So it should be okay. We have chosen the folder. We can add auto description for each diagram. We can even choose some font options here, make output, and it's going to run through the selected load cases and it's going to generate chosen components being M, Y, and F, Z in our case. Okay, so this is the result of diagram generation for you. You have all the cases that you have selected. So MY, moments, for example. I didn't open the shear force, but it doesn't matter actually. So important thing that is that you have these two options for generating diagrams for your report. These pictures are not dynamical, but if you generate them using the option dynamic report image and after you add it from report, it will be dynamical. So you have two options and whichever you prefer you can use. Sometimes I prefer it more just to generate a bunch of diagrams and pull it into my report. But when I expect to have a lot of changes, for example, we have some presentation to make and we go to our client and we offer him some solution and he wants others, so that's maybe the case when you would prefer to use dynamical report images. Okay, so beside graphicals, you have also result tables. For example, for tendons, you have tendon loss tables where you can easily choose whichever, literally whichever tendon you would like and generate through the faces. You can easily generate that just to see what's going on. Okay, this is only applying to the table, but if we want to see the graph, we should go here, and here you have all the tendons in the selected group through the construction stages. You can easily follow the changes in the force in the tendon through the stages. You can also select which step of the stage you want to see or even animate it if you feel a little bit lazy to scroll down. Anyway, really nice option here. You can also Sometimes it happens, but okay, we didn't lose anything. Probably it's my weak laptop here. So this is the point. Actually, we can add it to report browser, name it, and we can insert it as a dynamic report change. And let's say, for example, I want to change the force in this tendon. I make it lower. I don't have to picture everything, to take these charts or something. I just need to update my dynamic report and it updates automatically with it. Also, you can save graph as image, which is not dynamic then, and you can also save it as a text and then use it to maybe generate graphics in Excel. It saves as a CSV file. So basically, what more is interesting about this type of structure is to check the displacements. And in general, what is really characteristic about free balanced cantilever method is camber control. You could easily make a 2-hour webinar on this topic, but for now we're just going to say that it's really straightforward and easy to do the camber control in Midas Europe. It has dedicated option for it. So in the results, in the bridge section, you have camber reaction. You choose free cantilever method camber and you say FCM camber control. You need to define groups, 3 groups actually. The first one is the superstructure, the other is support node. That means all the top points on the pier and supports, and also you need to have all the key segments, these locking segments, in one group. You see here, okay. So you can view this in graphical or in table, but say okay. And you can see, well, maybe at first this diagram doesn't tell you much, but actually you can follow it along the bridge structure, superstructure, and see how it behaves along the bridge axis. So here you can simply select superstructure group containing key segments, bridge girder, and support nodes. Simply apply, and you can view in tabular form the formations that are going to be used for Camber. So if you go, for example, displacement contour, check everything, just say I want to see it in millimeters. You want to see minimum and maximum values, and let's say fix, active fix and zoom fix for stages are on. When you go to the phases, you will be able to see actually how it works. So we want to see only vertical deformation, and we want to show, of course, but not like this. It's too exaggerated. Let's say like this maybe. .05. Okay, it looks a little bit more normal. So you see that with each step, the structure is more and more deformed. And if you don't know what you're doing, you might ask yourself, how are we going to make it flat for our bridge? Which might not be a big problem for the railway bridge, where when you have ballast, but generally you want your structure straight. This is how it comes. Generally, you can see a little differences in height. Also, this pier has more height than these two neighboring, so it has more elastic deformation on it. Good enough reason for this difference in height to appear. You can see how the segments work. So this is it, but if we activate the current step displacement, it's going to apply our pre-camber, which was actually entered as a load, target load. So everything is nice and smooth in the end. So actually this pre-camber, simply put, is designed elevation of the span plus the necessary overheight. And usually we want our top surface of superstructure to be straight, to be flat. So this would be considered as designed elevation, and necessary overheight would be a pre-camber, which we get by setting the formwork actually to the correct position. Okay, so now that we are satisfied with our results here, we can even take a quick look at the design of the cross sections for the superstructure according to Eurocode. So usually in the results tab we have load combination tool, where you can actually use if you want auto generation, but it's going to, here we choose Eurocode. Where is Eurocode? Here. We choose, of course, both static load cases and construction stages. We want load factors to be both favorable and unfavorable, and we would like also to have option for rail traffic, but we will not use this option now, because at first it's something like Wizard. You generate your load combinations and then you filter it through some iterations, and you see which are not important, you delete them. So in this way you might get up to 3,000 or 4,000 of load combinations. We don't want that now, because if we let the design run on that large number of combinations, it's going to really take some time to be finished. So what we are actually going to do, we are going to use our predefined load combinations for this bridge, where actually a lot of these are already generated, but they are really filtered out. So actually we have here serviceability load cases for characteristic, frequent, and quasi-permanent, and also we have ultimate limit states and seismical combination. But maybe we don't need this seismical, because we are not going to treat columns in this at this moment, and we didn't take into account vertical excitation of the superstructure. So to make it more simple, we will paste. Okay, sometimes it happens that accidentally in Excel you mark more cells that you can fit here, so it doesn't want to paste it automatically. So you need to go back to your sheet and select it again carefully and then paste it. So here we have our serviceability and ultimate limit state cases. Now we will go to PSC tab. We will, in design parameters, sorry, we will choose everything here. Ultimate limit states, all three options, and serviceability limit states. We'll say OK. We expect some things not to go well because we had those tension in some area, or maybe we didn't provide enough reinforcement for shear forces, but it's something that we can easily fix by just adding more reinforcement to the section. Okay, we have to define which are our serviceability cases for characteristic. Here, frequent and quasi-permanent. We confirm this, and we need to choose our design and output stations. Let's see, previously we had something selected, so basically up to element 87. Maybe it's too much. We wanted just to showcase it quickly. So for example, let's choose a few elements from the midspan, a few elements from the pier. We will apply, we will check the results at both ends of the finite element. Let's say apply, and let's say perform design. So what the software does currently, it is running for the selected elements, it is running a check for the ultimate limit states and the serviceability limit states. Hopefully it will not last too long. Okay, so this was quite fast. So let's check the results. Here for the fluctuator we can see, okay, we'll just adjust the units. Yeah, okay, we have some small problems here, but it's nothing to stress about. This can be easily managed. Here we have some problems, but we can actually add more reinforcement into the webs of the cross section near the columns. Basically, we're running out of time, so I will devote more time to going into detail about these results. But in general, they're not really so problematic. Here we're just going to run through the stresses for cross-section at construction stage. Again, change the units. Okay, here we have smaller this for example, we could easily satisfy this with adapting bigger concrete class or readjusting the position of the tendon's profile. Here also. Okay, let's not select all of them. It's going to take a lot of time. Maybe just first 100. Yes, okay, we actually didn't expect to have any problems with stresses in the pre-stressing tendons. Let's see. Check for service loads. Everything is satisfied. This is nice and clean. Principal stresses at construction stages also should be okay. They are. Principal stress at service load. Also all criteria is satisfied. So maybe just to show you one more option here, we have okay, here we can select position for PSC output, and for example, let's see first what have we chosen for. Let's take this one, for example, 18. You can simply enter it here, press enter, and if we click on Excel report, we are going to get a nice report about the PSC design for chosen element. Of course, you can do it for multiple elements, but just for this presentation, we're going to show it on one example, one element. This might take some time. Okay, the report is generated, and here you can see how it goes through all the clauses of Eurocode 2 to check for compliance. This is our element number, position is on the start of the beam. Here we have sectional information, material information, tendon profile information, also ultimate moment resistance, and of course complete check for all the tendons in the chosen member. Here we can see negative moment control. Basically everything is okay. Or maybe we have this little problem with shear forces, but as we said, we can provide more shear reinforcement and deal with it in that way. So basically this will conclude today's webinar. Thank you all for joining, for attending. If you have any questions, I will be more than happy to answer all of those. with email, so please, anything that you're interested in, or if you have some questions, please feel free to ask them. Okay.